As we gear up for TWIML AI platforms, now less than 2 weeks away, I've been out and about talking up the importance of automating, accelerating, and scaling machine learning and AI in the enterprise. Now, I'm usually the one doing the interviewing, so being on the other side for a change was a nice experience. Much thanks to my friends Alex Williams, host of the New Stack Makers podcast, Minter Dial, host of the popular podcast Minter Dialogue, and James McGuire of Datamation. I had a great time chatting with each of them, and I encourage you to check them out via the TWIMLcon blog at twimlcon.com/news. And while you're there, be sure to check out the latest speakers and agenda updates, and if you haven't already registered, take that step to secure your ticket for what's shaping up to be an amazing event. And now, on to the show. All right, everyone, I am on the line with Mark Ryan. Mark is the author of Deep Learning with Structured Data, a book that is currently in early access with Manning and due for publication in the spring of 2020. Mark, welcome to the TWIML AI podcast.
Thanks, Sam. It's great to be here.
Awesome. Let's get started by talking a little bit about your background and, in particular, deep learning with structured data. That is a topic that folks are starting to talk about. And in fact, via the meetup group in association with the podcast, we have a fair amount of experience exploring this through the Fast.ai study groups that we do. That's a big part of one of the lessons in that course. But I'd love to get a sense for, how you came to be interested in this particular topic enough to write a book about it.
Sure, Sam. So my academic background is from artificial intelligence a couple of winters ago. So I studied at U of T with Graham Hurst back in the late 80s, and it was all symbolic AI back then. And there were some interesting use cases, but it to a large extent it didn't work. And I went to work for IBM. Had a great career there, learned a great deal, spent a lot of time in DB2, the relational database product from IBM. And about 2016, it became evident to me that artificial intelligence was starting to work. Mm-hmm. There were things that were actually working, became general knowledge, and that reignited the spark in me. So I did Andrew Ng's intro course and the Fast.ai course. So it had that as my introduction to deep learning. And I was very interested in deep learning and the promise of that. And one of the things I found a little bit frustrating is a lot of the use cases, particularly outside of the context of the Fast.ai course, were to do with images or audio. They weren't structured data. And what I was looking for was, can I find a way to use this in my day-to-day work? Because this looks like it'll be very useful, and I wanted to learn more about it. And the best way to learn about it is to use data sets that you're familiar with. So when I did the Fast.ai course, and this would have been version 1 of the course, so it's been through a couple of iterations since then. Yep. And there's the section on doing deep learning with structured data, and that really sparked my curiosity. I thought, wow, this is really cool. So I began to look around for some code to have as sort of a starter kit to get going, and it wasn't easy to find. But there were some Kaggle competitions where people had been working on structured data sets and applying it to deep learning, and some very elegant little kernels
like that Rothman stores and the like.
Exactly. And I was really impressed by some of the work that I saw there. It was very elegant, very, very straightforward, and good for me at the stage I was at then to get started, start doing some coding. And at the time, I was responsible for the support organization for DB2. So there's tons of data there, hundreds of tickets coming in every day, lots and lots of data. And I thought, it would be good if we could apply deep learning to this to sort of see, can we do some predictions that are useful? So I built up a prototype model to predict how long a ticket would take to get closed. And that, seemed it worked reasonably well. And then did another project, sort of taking what I've learned to predict duty manager calls. So those are cases where a client reaches a point of frustration and says, "I'm done. I want to pick up the phone and get something happening with this particular problem." So applying what I'd seen from some of the kernels in Kaggle and using the data that was available, created these prototypes. And I've learned a lot doing that. And they were, I think they turned out fairly well. But one of the problems with those prototypes was that the data was obviously proprietary. It couldn't share that. And there's a very strong ethic, as you know, in machine learning and data science to share results.
Mm-hmm.
So I started to look for a more, it's like a general data set that I could use to apply deep learning to structured data. And I've written a few blog posts on Medium about my experience with the predicting time to resolution and predicting duty manager calls. And Manning got in touch with me and said, "Would you like to write a book?" Kind of pulled this together, and I thought, "Wow, that sounds interesting. Sure."
Hmm.
It has been a lot of work. It's and I've certainly learned a lot in the course of doing that. And one of the things I've done is create sort of a full end-to-end example using an open data set, which is to do with streetcars in Toronto. Toronto's my hometown now, and it has a very extensive streetcar network. These are light rail system that runs on the regular roads, and they're great. They're efficient. They're relatively cheap to run. They're cheap to create, much cheaper than subways. The problem is because they share the roads with regular traffic, if they break down or there's a delay, it really exacerbates gridlock. So the City of Toronto publishes a data set that describes all of the delays that have happened for the last 5 years. And I thought, well, I'm going to roll up my sleeves and try to create a simple deep learning model to analyze this data and see if we can come up with predictions to predict where there are going to be streetcar delays and hopefully be able to prevent them. So that was kind of the path I took, and that was the genesis for the book.
And so, should I assume that that worked? That you were able to come up with a model that predicted the streetcar delays or predicted streetcar delays with that data set?
Yeah, it does. It does a decent job. It's not a huge data set. There are about 90,000 records right now.
Okay.
So there's some limitations, but certainly for the purposes of helping somebody who's going to be taking a trip, it's the accuracy is good enough to be useful. But more importantly, in terms of as a learning exercise, I think it's useful because it's an open data set. It's big, but not so big you have to deal with kind of the problems of big data. It's very messy. So
Mm-hmm.
there's a lot of work to be done to prepare the data, which I think is a good learning experience. And it has various different kinds of data. There's text data, there's categorical data, there's some continuous data. So it has a lot of it's big enough to be interesting, but not so big that it's overwhelming. And I think it kind of makes a decent end-to-end example to go through the topic.
Awesome. Jumping back to the couple of projects that you worked on when you were at IBM, in particular, this looking at how long it took to close tickets. When I think of a trouble ticket use case, and when I think of that trouble ticket use case, I think of, not just structured data as being useful, but also the content of the ticket itself. So textual data, more like the application of NLP. Did you use only metadata about the tickets to predict the close time, or did you also use that content?
That's a great question. So I did use the content. There's all the tickets had a description. The description could sometimes it be 2 lines, like you suck. A little bit more elaborate than that. And sometimes it would be a paragraph of lots of detail. But that description was really essential because that's kind of the initial customer's sense of what they found. And we had a simple. The model included a simple recurrent neural network to deal with that data. So it that text field was tokenized, used embeddings. And then there was a layer, an RNN layer that was applied in the overall model to take that text into account. Mm-hmm. And it was interesting, the difference, because they did some experiments of including that as a feature and then excluding it, because it was fairly expensive. It added some length to the time it took to train the model. And it made a reasonable difference. Like it was between 3 and 4% the accuracy if this field was included. And that really excited me. I thought that's really something. And the other thing is that these descriptions weren't all.
So the particular field is the description field. So all of the text of the ticket.
No, it's just the description. The text of the ticket wasn't available to me at that time. So it wasn't the
Oh,
full
okay.
back and forth. Sometimes that like there could be the equivalent of 100 pages of text. So all I was dealing with text wise was the description. So it could be up to 500, 600 characters
Got it.
altogether.
Got it. And so that's typically the textual description of the issue, either as provided by the initial uh, customer who's submitting the ticket, or whoever the support rep is that is taking their call.
It would always be the customer, and that was
Okay.
it was intentional to say, and that was part of the whole idea of the model, was to only take data that was available when the ticket first hit our system.
Okay.
So, and that description would be there. There were other things, obviously, like whether the ticket had changed in severity, that wouldn't be available when the ticket was first opened, because that's kind of a data leakage problem. You start to peek over and see, oh, that looks, you use data that you don't actually have available to you when you're making the prediction. But the textual description of the problem coming from the client was always there when the ticket was opened, and that was one of the features that was fed into the model.
Okay, and so you said that the importance of this feature, this feature's presence gave you an additional 3% increase in accuracy. That is, relative to what without it? How much of an impact did it have?
So that was in terms of the absolute accuracy. So I think at that time it was probably going from 73 to 76% accuracy,
Okay.
taking that field out or leaving it in.
Which I think says a lot about the power, I guess, of doing deep learning with the structured data, that adding the text, the descriptive text of the ticket only gave you an incremental 3% accuracy in terms of predicting how long it'll take to close the ticket. Is that reasonable? Is that your
right.
interpretation as well?
That's right. I guess at the time I saw it, it's relative to where you are. I was very happy it had that increase, but you're right that the portion of the data that would have traditionally been dealt with deep learning was only one of the feeds that was going into the model. And that feed by itself, while it made a difference, it was a relatively small proportion of the difference in terms of the accuracy.
Yeah. I would have thought that without the text, it would be very hard to solve this problem with any degree of accuracy. Interesting. And out of curiosity, did you try training a model only on the descriptive text to see if you were able to get any results? I'm wondering if there's a scenario where if you didn't have it, if you added it, it only gave you 3% incremental accuracy, but you could get a good part of the way there if you didn't have any of the other things either.
That's a really good question. I didn't try that, but that's an interesting question. I guess in this, may be kind of a primitive way of thinking about it, but because there were, there were another 13 or 14 features that were available, and sometimes this text was fairly short, I thought, well, this will it'll have some impact, but by itself, it probably wouldn't be enough to actually come up with a reasonably accurate description. And then just looking at some of the descriptions, they were pretty cryptic. But something I just wanted to mention is that these descriptions weren't even all in English. So there were a fair number in Japanese or Chinese, and just given the aggregated size of the data set, it wasn't massively huge. It was about a little over 1 million records. It still made a difference. Like, it still provided some benefit. And I see that. I know some people are kind of critical of the idea of using deep learning, kind of backing up the dump truck of data and just tipping it over and seeing what comes out. But at the same time, I was impressed by what could be done without doing a whole lot of monkeying around with the data. It was just sort of taking the structured data as it was, applying a relatively simple model to it, getting not bad results. I was impressed. I was impressed by that, and particularly because there had been so little, other than the Fast.ai course, so little spoken about in terms of using deep learning with structured data.
Mm-hmm. Mm-hmm. So we tend to think of, rightly so, deep learning as requiring a ton of data. It's certainly exacerbated by the fact that some of the things that deep learning is really good at are, images, which can be large, speech, which can be large files. Structured data can be a lot more compact, but when we think of the number of rows or examples that you're feeding into a model do you require less data from a examples or rows perspective to train a deep learning model accurately on structured data, or is it kind of about the same, but the data is just more compact?
That's a good question. I'd say that to get sort of the rule of thumb, that you need tens of thousands of records to have a starting point is probably applicable, as applicable to structured data as it would be to unstructured data.
Mm-hmm.
Um, but it's interesting. One of the things I heard as a critique, because certainly there are people who said, like, don't use deep learning with structured data. And I'm thinking, well, why? Because that's where my problem space is. That's where the job I'm trying to do is all about structured data. Yeah, don't use that. Use XGBoost. Use something simpler. And I said, well, why? And some of the answers I got back were, well, the structured data sets are too small. Like, they're not big enough to actually apply deep learning to. And I think that's a bit of a canard, because there are some huge structured data sets. Their data sets, certainly in the world of DB2, which is all about structured data, so structured tabular data,
Sure.
commonly had tables with billions of records in them.
Mm-hmm.
So that objection, I think, is a little bit it's a little bit short-sighted. And obviously, you're not going to get great results with tiny data sets, whether it's structured or unstructured. But I think as an objection to attempting to use deep learning with structured data, the data set size really is not material to the decision about whether it's worthwhile or not.
Did you attempt to apply XGBoost or any other method to this kind of problem?
I did. So I tried XGBoost on two of those problems that I described, and I guess one thing that is true, the results were not significantly better for deep learning. So I think that's one of the arguments people say, well, it's not a great idea to use deep learning with structured data, is if there's a simpler way to do it that doesn't have the complexities or the opaqueness of deep learning, then why not do that?
Right.
And I think there's something to be said for that. But at the same time, if I'm looking down the road a little bit, the amount of effort that it takes to get reasonable results with XGBoost versus deep learning, particularly the human effort required for it, I'm not convinced that XGBoost for example, is going to be the winner there. As there's been so much attention on the efficiency of tools related to deep learning, the libraries are getting better. The TensorFlow 2.0 coming out, making things much more straightforward and simpler. I think some of the objections are a little bit out of date, and there are certainly cases where a non-deep learning approach could produce better results and maybe the right way to go. I guess the argument I'm making is that people should keep an open mind about applying deep learning to structured data, and I think particularly as the human cost that's required to get results becomes a bigger and bigger factor, we may find that deep learning has more applicability to structured data. To keep an open mind about it.
Yeah. No, that's a really interesting point. I think we've got an entire conference coming up on the tooling and technology platforms that are allowing enterprises to increasingly automate and make their ability to deliver deep learning models into production, as well as traditional machine learning models into production more quickly and efficiently. And I think that's only going to serve to reduce the barriers. And as you mentioned, the frameworks are getting more powerful and easier to use. And so now you've got this, yes, kind of a more opaque method, but one that is highly automated in a sense that you don't need a lot of manual feature engineering to get good results versus one that requires a lot of human investment to get the same level of results or comparable results. As that barrier to entry on the deep learning side is reduced, in addition to all the software tools and frameworks that are improving, you've got hardware that's making it cheaper to build these models on the compute side. That's really going to tip the balances. That's what I'm hearing you say.
Yeah, I really believe that's the case. And I think, and this is something in the Fast.ai course, Jeremy Howard said that this topic, people have kind of scratched the surface of it. And I think there's much more to be done there. And obviously, my approach, I'm trying to, is sort of a meat and potatoes, trying to solve problems approach. But I'd hope that there were some research as well, people looking at it from a research point of view, or saying what can be done. And the other thing that I think structured data has, there's sort of by definition, structured data has very rich metadata. So you have a database where everything, all of the tables in the database are described in tables, and it's all tooled and instrumented to be able to see what everything that's there in the database. And I think there's some potential for work that's kind of exploratory. I could see something like a web crawling to go through a database and see, is there potential for a useful model here? And you can see a situation where, as the cost of compute drops, have something that's running in the background and sort of trying all sorts of different combinations of features in a large database, say, oh, maybe get some interesting results there. And being able to do that, and that's something that structured data gives you that you don't get from unstructured, what you don't necessarily get from unstructured data, where there isn't that sort of rich metadata describing what's there.
We'll come back to the structure in just a moment, but you mentioned one of the points that Jeremy makes in the Fast.ai course, and that is that in many of these examples, particularly the Kaggle ones, like I think it was Rothman Store's competition, when you look at the leaderboard, I forget the details. I'm going to botch them. I think, out of the top, the top N, a good number of them, if not the top spots, were folks that, applied deep learning based approaches. And the key takeaway is, and this is, them competing against data scientists with, oodles of experience in this particular retail domain, and in many cases, folks with no domain experience plus deep learning were able to outperform folks that brought domain experience and handcrafted models to bear.
Yeah, that's a good observation. And Kaggle in a way there's some artificial aspects of it, but it's raw capitalism, and what works best rises to the top. So yeah, I think there's potential there, and some of the big players are doing this, and there are applications that I've heard of. Google and Amazon are doing with structured data, but it just doesn't seem to be something that's really front and center in terms of what people, as they're learning about deep learning and where the research is. It seems to be much more on the unstructured, that is the non-tabular data side. One of the other objections I've heard is that there's this heuristic thrown out there that about 80% of the data in the world is unstructured. So, if that's the case, if it's only like 1/5 of data is structured, then, how interesting is it to apply that?
Still a lot of data.
It's a lot of data. And I know from experience from working with DB2, I know that the world runs on it. Every bank, every insurance company, every government depends on structured data. Relational database may not be sexy, but it underpins our modern lives. So there's a lot of important data that's structured as well, even if the volume isn't as much as unstructured data.
Mm-hmm. You were making the point that it's the application of deep learning to structured data in particular is a topic that doesn't get a lot of play out there, and it made me think of embeddings, which is one of the key techniques that are used in applying deep learning to structured data. When I first heard about embeddings through the Fast.ai course, I don't know, a couple of years ago now, you didn't hear a lot about it. It was in a couple of obscure papers. And now everybody's doing it and talking about it, and it's almost passé, right? It's just a tool that we pull out of the toolbox to solve a great number of problems. There was just an article I saw yesterday about Stitch Fix, the kind of clothing styling in a box subscription company, created a model. It was talking about some of the different models that they use internally, and a lot of them are based on style embeddings and things like that. And so, kind of in that vein, I suspect that we'll start to hear a lot more about this. And the Fast.ai course is just kind of ahead of its time once again. But why don't we take a second to drill into some of the, how it works and kind of the details that you'll be talking about in the book. It's a Manning book, so I'm assuming it's going to be kind of roll up the sleeves and kind of dig into like how to make all this stuff work. And I would assume that embeddings is a big, one of the chapters in that book somewhere. Is that the case?
Absolutely, absolutely. So dealing with, I guess one of this may sound a bit trite, but when I first heard about one-hot encoding, I thought, I hate this idea. And I know it's necessary. I know it's something that we have to use. But I thought, wow, this is, if you've got a category with more than a dozen values in it, this just gets crazy. You end up with these huge, pandas data frames, for example. And embeddings give you a way you can assign integer encodings to the values in a categorical feature, and then use embeddings to learn the relationships. So you get away from having to use a one-hot encoding and the inefficiencies that are involved there. So so I just in terms of what you said about embeddings, completely agree. It's a very hot topic, and the idea, I think the idea that something that came out of NLP and has more broad applications is really interesting. And the idea that you kind of get unsupervised learning, not for free, but as some of the exhaust fume from doing supervised learning, solving a supervised learning problem, and you can use the embeddings to come up with categorizations, like movie categorizations for Netflix, that kind of thing. And that's really interesting. You get a bit of a 2-for-1 value.
One of the things that comes up frequently in our Fast AI study groups as a point of confusion when we're talking about the structured data topic is kind of the relationship between embeddings from an embedding space perspective and the way it's used in NLP and the embeddings that we use in these structured data problems. Do you have is that real clear to you? Do you have a great way of explaining that?
Well, I guess with an NLP, you can have tens of thousands, millions of values, just the number of individual words there are, each with their own individual embeddings. And then in a structured data problem where you're leaving aside textual features, just talking about categorical features, you're going to have a smaller number of individual values. So the embedding space, you may have a smaller dimension. You may have, if I could say, a simpler embedding space than you would dealing with NLP. But the fundamental idea is the same. And I guess to get back to your question before about how things work. So as I mentioned, the book has the Toronto streetcar data set as the problem that's being solved. So go through the process of cleaning that up. So getting rid of bad values. One of the things that I've learned over the course of doing this was some geocoding. So there are address values that describe where the problem occurred, or where did the streetcar break down, where was there a delay. And those address values are just completely messy. They're totally free form. Say young and queen. They're misspelled. They're references to sort of known areas in Toronto. So it's great. It's a very interesting problem to have. And it took advantage of Google's geocoding API to turn those values into latitude and longitude values. So that's the feature that required the most effort to get something coming out the other end. And then for the categorical values, so that would be, for example, the streetcar route, the vehicle number, the day of the week, so Monday, Tuesday, Wednesday, whatever. Those get translated to integer IDs, and then so all the categorical values get translated that way. Text fields, individual words get translated into IDs. And then those get prepared to be fed into a fairly simple Keras model. but I guess the thing that is a bit of an innovation is that the layers in the model are automatically defined based on the columns that are in the table, the input table. So if and all of the categorical columns get a set of layers in the model, they get an embedding layer and a number of other layers. If there are any text columns in the input data set, they get embeddings. They also get an RNN layer, and then continuous values like temperature just kind of flow through. So that model gets built up layer by layer automatically based on the columns that are in the input data set, and that's, in a nutshell, how the model gets put together.
So this automated generation of the model, is this based on a tool that you've built?
This is just Python code. So there are there's part of the code is identifying which columns of the overall data set, which columns are going to be used to train the model, and then saying which columns are, breaking them into three categories. Categorical, so those would be things like the day of the week, continuous,
Yep.
like temperature or time duration, and text, so a description of a problem, for example.
But it sounds like you've built this tool that you point at a data set and it will, almost like AutoML, like create a model that, at least as a starting place for making some predictions on the structured data, as opposed to, the book walking you through like how you would perform this analysis by hand.
That's right. So the book provides, the idea of the book is to generalize a little bit. So the streetcar problem is used as an example, but saying more generally, here's how you deal with it. But the intention of the code is that it could be applied to other structured data sets.
Mm-hmm.
That it wouldn't be limited. That somebody could fairly quickly take a different structured data set and apply the code and try it out to see how it would work with a different structured data set with different columns and a different mix of categorical text and continuous columns.
Okay, cool. And how are the chapters structured? Are they different features of this? Are you building up this Python code, or do you assume it from the beginning and you're, talking more theoretically about these topics? How do you organize things?
So Manning's pretty big on being practical. So they certainly encouraged me to stay close to the code. And this is one of the things, and I know that you've sponsored a number of sessions going through the Fast.ai course. So you've seen that ethic there of really trying stuff that, you get as soon as you can, try to apply it in code.
Mm-hmm.
And I've tried to do that in the book as well. So introduce bits and pieces. So talk about pandas data frames is one of the essential items. So I spent some time on that. Talk about the data set. Talk about the different steps you need to take to clean up the data set, including the geocoding problem that I talked about before. And then a chapter on how the layers of the Keras model are automatically put together. And that's one of the ones that's not that I'm working on currently. Will be released a little bit later in the year. There'll be a section, as you said, talking in a bit more detail on embeddings, what role they play. And then the other thing I really want to do, and this has been quite a challenge, is have as end-to-end a process as possible. So be able to talk about here's how you deploy the model, and here's how you get a little website that would let you pop in the description of a particular trip and get the prediction back whether or not that trip would incur a delay. Because that's one of the things that I found in terms of my learning process. There was an awful lot that kind of took you up to the point where you had trained the model and had some sense of its performance, and then things got a little bit sketchy about how would you actually deploy it? How would you get it into not even production, just get it to the point where somebody else could use it or play with it. So I definitely want to spend some time talking about some options for doing that and taking the reader through a particular process for deploying the model.
Oh, that sounds awesome. And so you've kind of suggested this, but the early access process or program at Manning is one in which you are kind of incrementally posting chapters of the book, and folks can kind of buy in early and get access to these chapters. Is that right?
That's right. So they get access to the book, and they get the completed book. The other part of it is it's supposed to be a two-way thing as well. There's the opportunity to make comments and to frame the book, either to say things that need to be corrected or adjusted, or make recommendations for topics that need to be covered later on in the book. So people who get involved early, who take advantage of this, have a chance to really not just be sort of passive participants, but also contribute and be part of making this book or other books that are in this program successful and meet the needs of the people who will be reading them.
That's awesome. Yeah, one of the things that really jumps out at me in this conversation, we keep kind of coming back to Fast.ai, I think, because, I've seen it impact a lot of people, myself included. And, I'm seeing in this conversation, how the echoes of that course are clear, and, what you're doing here and kind of extending what you got out of that course now into a book. And that's exactly, how the course is kind of designed, that there's a lot of self-direction required to go through the course and really get the most out of it. And a lot of that is taking what's taught and applying it to things. And so that is awesome to see.
It is a great course. It's a fantastic opportunity. I really think I learned so much going through it, and also seeing it comes up in all sorts of different contexts as well. I mean, in the sessions that you've sponsored, other people learning about deep learning, and I think it's not just the course; it's also the approach to teaching. That saying, like, get to the coding as quickly as possible and try different stuff. And he's pretty bold as well, in making a number of significant changes in the platform being used. That's a lot of work, and there's risk in that. But I got to tip the hat to the team that puts that course together. I think they've done a really fantastic job, and had a really big impact on the industry and on people's lives. People have learned a lot. It's been a ladder up for a lot of people into a world that's really exciting and really interesting and really important.
Yeah, absolutely. And I would encourage anyone who hears us gushing over this course and is interested in taking the course to do so. And Jeremy Howard, who teaches the course, always says that taking the course is best done with other people. The people that do that are more successful. And that's really why we, with the support of a bunch of very dedicated volunteers, have been doing, can't even count now how many kind of cohorts of folks we've done through the various versions of the course. There are several versions, and then a part 1 and a part 2. But hundreds of people now have participated in our study groups to just get support in working through these courses. If that's interesting to you, encourage anyone who's listening to visit TWIMLAI.com/meetup. Sign up for the meetup and express interest in the study groups. And if we don't currently have one running, when you do that, raise your hand in the Slack channel, in our Slack, and express some interest. And we tend to kick these things off, when folks are interested in them. So, with that, Mark, thanks so much for taking the time to share with us about the book. It sounds super interesting.
Thank you, Sam. And Sam, I want to also thank you for the podcast. I've learned so much. Been a faithful listener for several years now, and it's been a great asset. I learned a great deal. So thank you very much for all the work you do to get the podcast out. Really appreciate it.
Wonderful to hear that. Thanks so much, Mark.
Thank you.
All right, everyone, that's our show for today. For more information about today's show, visit TWIMLAI.com/shows. Remember, less than 2 weeks to register for TWIMLCon AI platforms, so head over to TWIMLCon.com now. Thanks so much for listening, and catch you next time.